Hey there, let's look at lesson 17. So the goals today are to find the inverse of a linear function given, given in function notation. Also, write a linear, you can see how well I type, or poorly, and an inverse function. Hold on. Sorry, I got distracted again. So our goal today is to both find the inverse of a linear function given in function notation and write a linear function and an inverse function to model data and solve problems. So we're getting towards the end of the unit. We're really pushing you guys to write your own equations and be able to find the inverse of them. So water in a tank. A tank contains some water. The function W represents the relationship between T, time in minutes, and the amount of water in the tank in liters. The equation W of T equals 80 minus 2.5 T defines this function. Discuss with a partner or listen to me talk. How is the water in the tank changing? Be specific as possible. I would say our tank is decreasing, right? So for every minute that goes by, it's decreasing by 2.5 liters. So here, it starts out with 80 liters in the tank. 80 liters in the tank, and it's losing 2.5 liters every minute. That's what that equation describes. What does the W of T represent? Is the W of T the input or the output? So the W of T is the output. The input is the time. Okay, our independent variable is the time. So for every minute that goes on, the tank decreases by 2.5 liters each minute. Okay, so we start out with 80 liters and we're losing 2.5 liters a minute. Okay, WT represents the amount of water at time equals T, and that was minutes. And then T is the time in minutes. Time equals our input. And W of T equals our output. Sketch a graph. Be sure to label the axes. 10, 20, 30, 40, 50, 60, 70, 80, so I can go by tens. So this equation right here would be oh goodness, that was supposed to be an A. Amount of water, I should say the units, in liters, the amount of water in the tank, 10, 20, 30, 40, 50, 60, 70, 80. And here is time in minutes. Look, so 5, 10, 15, 20, 25, 30, 35, 40. So every minute we lose 2.5 liters. That means every 5 minutes we would lose 12.5 liters. I just did 2.5 times 5. So if we start out with 80, that's what time equals 0, we have 80 liters. And let's see where we are at time equals 10. We're at 55. So I just did 80 minus 2.5 times 10, and I'm at 55. So at time equals 10, 40, 55. Now let's do time equals 20. I'm just trying to graph it, plot some points. So when my input is 20 minutes, 80 minus 2.5 times 20, 30. So 20 minutes, I'm at 30 gallons. So I went down, let's see, 10, 25, 5, 10, 20, 10, 25. So at 30, I'm going to be right here. And how much time does it take to empty it? Okay. I cannot draw straight lines with this. It's just hand drawn on my tablet. Cool. So sketch a graph of the function. Be sure to label the axes. This is actually 32. And I just did, this would be, what did I say? 30. Now, when I want to know if it's empty, I want to know when there is 0 water left in the tank. What time is it when there's 0 water? All right? So I'm going to subtract 80 from both sides. So I have negative 80 equals negative 2.5 t. Divide both sides by 2.5. Negative 2.5, and I got t was 32. So it took 32 minutes to empty the tank. Okay? All right, another look at the tank. A tank contained 80 liters of water. The function W represents the relationship in the equation. All right, so now we're going to take another look. How much water will be in the tank after 13 minutes? So we know 80 minus 2.5 times 13. But this is what we did to sketch it. So 80 minus 2.5 times 13 equals 47.5 liters. How many minutes will it take until the tank has 5 liters of water? All right, so when the tank has 5 liters of water, even though it started out with 80, how much time does it take? When I wanted to know when the tank was empty, this is what I did. Okay, so now I'm going to solve for t. What we're getting to is we really, it'd be easier if we knew the inverse function to do this. So I have negative 75 equals negative 2.5 t. Divide both sides, because we've already done this math once when we graphed the equation. But here we are doing it again because we didn't find the inverse yet. So 75 divided by negative 75 divided by negative 2.5 is 30 seconds, or 30 minutes. Yeah, which was right here. 30 minutes. Cool. In this situation, what information can we gain from the inverse function of W? So if we knew W equals 80 minus 2.5 t, if I subtract 80 from both sides, I'd have W minus 80 equals negative 2.5 t. So the inverse is the time. What time is it? Whenever the tank is whatever full, we can plug that into W and get what time is it. So I could walk up to the tank and read how many liters are left in the tank, plug it into this equation. Sorry, my pen got all confused. See, I'm not doing anything. There we go. plug it into this equation, and it would tell me what time it is, right? So that is the gain. If I want to know what time it is, given the amount of water in the tank, I'd use the inverse. If I want to know how much water is in the tank given the time, I would use the other equation. Find the inverse of function w. Be prepared to explain or show your reasoning. I just did. W or t equals w minus 80 divided by negative 2.5. Okay. How would the graph of the inverse function compare to the graph of w? Describe or predict or sketch your prediction. So we're going to sketch our prediction. I think I need to relabel my axis though. Yep. So we'd have a full another graph, time here, and amount of water here. So we know the tank was empty at 32, so 10, 20, 30, 32. Zero, 10, 20, 30, 40, 50, 60, 70, 80. So at 0 water, it's 32 minutes. And then at 80 liters of water, it would be 0 minutes. So that would be our straight line. Okay, as straight as it gets. And that would be the inverse. So to read that, we know at 0 amount of water, it's 32 minutes. And then as time decreases, the amount of water is going to increase. And then at time equals 0, we have 80 liters of water. And there it is. That graph is way better than mine. All right, phones and homes. 1 second. Okay, last one. So, in 2004, less than 5% of the homes in the U.S. relied only on a cell phone. Since then, the percentage of homes that used only cell phones has increased. We've talked about this in the past. Here are the percentages of homes with only cell phones from 04 to 09. Okay, suppose a linear function p gives us the percentage of homes with only cell phones as a function of years since 2004. Okay, fit a line on the scatter plot to represent this function and write an equation that could define the function. Use function notation. Guys, this is important. Okay, to be able to look at a graph and come up with an equation is super duper important for algebra. Okay, very super duper. I'm going to insert a line using this cool function so I can mess with it. This way I can just mess with it. So generally we want the same amount, like some dots above the line and some dots below the line. That looks fine. I know the first point and the last point are pretty far away from the line, but it's okay. So you guys would do this with a straight edge and a pencil. Fit a line, got it. Write an equation. So there's two things that we need to write an equation. One of them is the y-intercept. So we're using the equation y equals mx plus b. Now the y-intercept is the b, and I actually saw this the other day. A teacher helps their students remember it because it's the beginning. That'll work. Beginning. I don't think I'm spelling that right. All right, so right here, it's the beginning. Let me erase that circle, though. Okay. Let's see. 4, 6, 7, 8. So those go by 2s. So this right here would be 2. That'd be, I don't know, 4.1? Nope, to 3.8. It's just a guess. And now we need the slope, right? And the slope is the change in y. It's rise over run. It's the average rate of change. Average rate of change, slope, rise over run. So the change in y over the change in x. That triangle means delta, which means change. So since we're on these points, I'm going to grab them. So that's this one and this one. So we're going to do the change in y, which is the percentages. 17.5 minus 6.7 over, so we just did 75, and then we're going to do over 4 minus 1. 17.5 minus 6.7, divide by 4 minus 1, which is 3. And I get my slope equals 3.6. So my equation, that's not function notation. So let's see. Suppose P gives the percentage of homes, so we're going to have P as a function of years, which is time, equals M, which is 3.6 times T, plus the y-intercept. So slope and y-intercept. And that right there is the line that represents this function. Okay? P of t equals 3.6t plus 3.8. That's where we got 3.6. It's the slope, and 3.8 is the y-intercept. Now it says to use your equation to find the value of p of 6. 3.6, input 6 for t, plus 3.8. That's our equation, right? Yep. So 3.6 times 6 plus 3.8, 25.4. And then explain what it means. I didn't do that right. 25.4. Okay, that tells us the percentage of homes with only cell phones, six years after, with the original problem and read it, 6 years after 2004. Or you could say 2010. 2010. Okay? 25.4%, the percentage of homes with only cell phones 6 years after 2004, or 2010. Use your equation and solve it for t. I don't know why that's not going. Okay. I don't know what happened there. So use your equation and solve it for t. So p equals 3.6 t plus 3.8. So I'm going to subtract 3.8 from both sides. So p minus 3.8. And then divide by 3.6. So I get t equals p minus 3.8 over 3.6. what does this solution represent? So this equation represents the time given certain percentages. So if we know the percentage of houses that have cell phones, then we can figure out what year it is, okay? Suppose we want to know when the percentage of homes with only cell phones would reach 50%, 75%, or 100%. What equation could be written to help us find those percentages? Show your reasoning. So it would be that equation, okay? Sorry. I didn't actually finish this. It says when P equals 30. So we need the time when the percentage equals 30. I apologize. So 30 minus 3.8 divided by 3.6, and that would be 7 years after 2004, which is somewhere between 2011 and 2012. 30% of the homes own cell phones, okay? And then we could actually use this equation to figure out what year each one of those landmarks, or when each one of those times hit. So that would be your answer to number 4. I solved the inverse, and we could use that. We could find out what year our percentage was 50, our percentage was 75, and our percentage was 100. Very easily using that inverse function. Without doing all the subtract both sides, divide, etc. We're just going to use that inverse function. And I think that was it. Correct. All right, that was a tad bit long.